So I hope you can see the writing pad.
Yes, sir.
Okay. So let us say let us proceed with the problem that we were considering, the case of a parallel plate, rectangular channel instead of a parallel plate channel. So this is the rectangular section, and we set up the axis in the following manner. So y-axis and z-axis, and I'm just recapitulating the mathematical definition of the problem so that we can go ahead. So we decomposed the solution into two parts, u equal to u1 plus u2. u1 is the parallel plate channel solution, and u2 is what we are trying to obtain now by the following differential equation. Equal to 0. Pressure gradient term we have absorbed via u1, and the boundary conditions are at y equal to 0. You have this one. The dimensions, let us put, I think we considered these as A. So at y equal to A, you have u2 equal to 0. And in terms of z, at z is equal to 0. And z is equal to b. u2 is equal to minus u1, which is a function of y, because u is equal to u1 plus u2, sum total has to be 0. So out of these four boundary conditions, let us number this 1, 2, 3, and 4. We see that the four out of these three are homogeneous boundary conditions, and I just made a statement that because they are homogeneous boundary conditions, method of separation of variables will work. So why it will work, we will see. But before that, assuming that it will work, so we consider u2 as a function of y into a function of z. The objective of this is to convert the partial differential equation into ordinary differential equation. So with this, we can write the governing equation, this one, as f double dash g plus g double dash f is equal to 0. This means f double dash divided by f is equal to minus g double dash by g is equal to now. So if you see, this is a function of y only. This is a function of z only. This is equal to, so this must be a constant. So this constant, we give a name minus lambda square. So out of so many things, not about the variable or the name of the symbol of the variable, but square. So we could have put it equal to k or even lambda, but why minus lambda square? So lambda square, we by this, and lambda is real, so lambda square is something which is positive. That means by taking it symbolically as minus lambda square, we are taking it as negative. So this is negative. So the question is why we are taking it as negative. We will understand this immediately if we just take one of these equations and try to solve it. So we start with solving f and then g. So we will start with f. So f double dash. So let us write this completely. d2f dy2 plus lambda square f is equal to 0. This is the f equation. So this is a homogeneous second order ordinary differential equation. You can substitute f is equal to e to the power my as the trial solution. So this is m square plus lambda square equal to 0. Right. So this will give you a solution which is a function of this cos and sine. So if you check this one, m is equal to plus minus lambda I. So now because of this, so this I is square root of -1. So what we see here is that it means that f is e to the power I, say e to the power I theta, that type of expression. And we know that e to the power I theta is cos theta plus I sin theta. So essentially, you can imagine that f will have a cos and sine combination solution. So let us say that f is equal to some what we say c1 cos lambda y plus c2 sin lambda y. Okay, so this is f. Let us look into g. So similarly, you have let us utilize this space to write an expression for g. So d2g dz2, I'm writing this one, minus lambda square g equal to 0. So again, let us say f is equal to e to the power nz. If you consider it as a trial solution, then sorry, g, not f. So this will be n square minus lambda square is equal to 0. So n is equal to plus minus lambda. So that means here the general solution will have e to the power lambda z and e to the power minus lambda z, their combination. Again, e to the power x and e to the power minus x, their combination can be written as cos hyperbolic and sine hyperbolic, because cos hx is e to the power x plus e to the power minus x divided by 2, and sine hx is cos e to the power x minus e to the power minus x divided by 2. So in that way, what we can say is we could write this as c3 e to the power lambda z plus c4 e to the power minus lambda z, or instead of e to the power lambda z and minus lambda z, we can write it as a combination of cos h lambda z and sin h lambda z. So let us write the cos h and sin h. Just it will help in compactness of writing. Otherwise, e to the power and hyperbolic function you can write in terms of either of these two. So G will be C3 cos h lambda z plus C4 sin h lambda z. And our solution will be a product of F and G. But we are far away, I mean, little bit far away from getting the solution because we already have some constants and we have not yet found out the values of those constants. So to find out that, let us concentrate first on F. So F dependence will come from these two. So F dependence will come from, if you see, it will come from at y equal to 0. If you say the second derivative of this is equal to 0, that means d2f dy2 that is equal to 0. So if you have d2f dy2 equal to 0, so in that case, so I'm just freeing up some space so that I can write it here. At y equal to 0, you have, sorry, not d2f dy2, df dy. So, at y equal to 0, you have df dy equal to 0 from this. So at y equal to 0, so if you make df dy, cos will become sine and sine will become cos. Now the sine term at y equal to 0 will be anyway equal to 0. So this will become the sine term and this will become 0. So what it essentially will mean that so this will become the cos term. So at y equal to 0, cos 0 is 1. So that means you have 0 is equal to C2 into 1. That means C2 equal to 0. And similarly, if you consider at this one, so this we have used. I'm just putting up a tick because we have to make a check and balance of whether we have used the boundary conditions. So 1 we have used. Let us go to number 3, very similar for Z. So at Z is equal to 0, this will give dg dz equal to 0. And G is cos h and sin h combination. So at Z is equal to 0. So when you make the derivative of G with respect to Z, cos h will become sin h and sin h will become cos h with whatever plus minus sign. So now if that becomes 0, so this will be the sin h term, and if you substitute Z is equal to 0, that will become 0. And this will become cos h term. At Z is equal to 0, cos h term will become 1. So that means C4 equal to 0. So if we consider that boundary condition, let me write it here. So the boundary condition that at Z is equal to 0, dg dz is equal to 0, that will give you C4 equal to 0. So that means now we have used these two as boundary conditions, and we have got C2 and C4, these two as 0. So if you think that now we can write the product f into g as the solution, and in fact that was the whole idea. So f into g, what it will be? So f will have only c1 cos lambda y, and g will have c3 cos h lambda z. So c1 into c3. So what is this c1 and c3? C1 into c3 is some a. So c1 into c3, that will be a cos lambda y into cos h lambda z. So this f into g is this form, right? A is where a is nothing but c1 into c3. We have given it a new constant name. So now we have to use the boundary conditions number 2 and 4. So the boundary condition number 2, what it says is that let us write boundary condition number 2. At y equal to a, you have u2 equal to 0. Right. So at y equal to a, u2 equal to 0 means y dependence is coming from where? Y dependence is coming from f. That means at y equal to a, you have cos lambda a equal to So at y equal to a, your f equal to 0, that is cos lambda a equal to 0. Okay, so cos lambda a equal to 0 will give you a collection or a series of values of lambda which will satisfy this. So from basic school level trigonometry, you know it quite well that when this cos theta equal to 0, theta is 2n plus 1 into pi by 2. So basically odd multiple of pi by 2. So this means that we can write lambda a is equal to 2n plus 1 into pi by 2, where n will be infinite values of n. So lambda is equal to 2n plus 1 into pi by 2a. So what it means is that this equation, or rather this boundary condition, is satisfied not for all values of lambda, but for certain values of lambda. And these values are called as eigenvalues of the solution. So to give an emphasis that this eigenvalue is a function of n itself, we call it lambda with subscript n. Lambda with subscript n, just to indicate that lambda, for each value of n, you will have a value of lambda. So now for each value of n, you will have a value of lambda and you will have a value of this one. So once you have a value of lambda and a value of this one, for each value of lambda, you will have a collection of such terms. How many such terms? N number of such terms for each of these values of lambda. Now, because f into g is of this form, so for each lambda, this type of form is a solution. And because there are n such values of lambda, so a collection of those added together or linearly superposed together is also a solution. That means we can write the solution in the form this is just a linear superposition principle, that all the solutions with n values of lambda summed up together with some coefficient also becomes the solution. Individually they are solutions, but the general solution is a summation with the corresponding constants of integration multiplied. So this an is the reflection of the constant of integration. So in that way, we have arrived at the solution, except we could not so far obtain the value of this one, an. And remember, there are n such coefficients, not just a single coefficient. What we are left with, we have used boundary condition number 2 just now. So what we are left with is boundary condition number 4. This we have not used. So let us try to see what we get by using it. So boundary condition number 4, if we apply, so at z is equal to b, u2 is equal to minus u1. So minus u1 is equal to summation of an cos lambda n y into cos h lambda n b. This is just like a parametric constant because b is a constant. So this is what we get. But this alone, so this u1 is a function of y, we have to remember. This alone is not enabling us to find out what is an. So we will explore a bit deeper to evaluate the value of n here. So to do that, that is to find out the value of an. So whatever exercise we are doing here, the objective is to find out an. So we will write this one, the governing equation for f. So d2f dy2. I'm just writing it in a bit of a scattered manner with a purpose, because we'll write something in these intermediate free spaces. So this is equal to 0. So this is one of our, this was the governing ordinary differential equation for f. So now we have understood that not one value of lambda, but there are n number of such values of lambda. So if we put it lambda n, so if we put lambda n here, the solution that will come back from that will also be f for that specific value of lambda. So we call it fn. So this lambda n we have named as eigenvalue, and fn is called as eigenfunction. So now just to give all of you a flavor, I can understand there are a few mathematics students in this class, and they will feel it very trivial and straightforward. but I have to consider, so many students in the class who may not have equivalent mathematical background, and I have to give respect to that. So I will tell something which is in a simplistic way give a feel of what we are talking about as eigenfunction and eigenvalue. So forget about functions. In vector, all of you are familiar with eigenvalue and eigenvector. This is something which, no matter whatever is your branch in the undergraduate mathematics, all of you have done this. So eigenvalue and eigenvector means eigenvalue is something, a parameter value which is giving a non-trivial solution. Here also it is like that. So the value of lambda n, which is giving a non-trivial solution to this, is this one. So this is eigenvalue. The corresponding, so in this matrix algebra, if you have eigenvalue, then if you substitute that eigenvalue, okay, so that, say, in matrix algebra you have a system of algebraic equations Ax equal to lambda x. So what you are doing is you are having a matrix multiplication. It is via the eigenvalue is converting that, so it's a vector matrix multiplication. A is a matrix and x is a, I mean, we write it as a row or column matrix, but it is called as a row or column vector. So Ax in this case a column vector, one column. So Ax is equal to lambda x means this multiplication we are mapping to vector, this lambda x, where x is a vector and it becomes a scalar multiplier of the vector x. Lambda is a scalar, that is also a vector. So for each value of lambda, you will have it the corresponding value of x which satisfies this equation, and that is called as eigenvector. So similarly, here it's not vector space but a function space, because here our mathematical space of concern is not concerning a vector, but it is concerning function. So this is eigenfunction. So once you have an eigenfunction, it is just like the value of the value when substituted, the result which comes out from the governing equation as a function. So this is just very analogous to eigenvalue and eigenvector. Here it's a functional space, so we call it eigenfunction. So now what we do is we multiply this with Fm, where m is something not equal to n. So this m and n you do not confuse with e to the power mx and e to the power nx. It has nothing to do with that. It's just two independent symbols. So what we do is we multiply by Fm and multiply with dy and integrate. So integrate from the limits y is equal to what? Y equal to 0 to y equal to a. That is our domain of y. Okay. So now this integration we will carry out. We will integrate this by parts. So when we do integration by parts, we always when we have to consider something as the first function and something as the second function. What we normally do, see, the rule of the integration by parts is first function into integral of the second. So higher derivative will be integrated and we can consider this therefore as the second function and this as the first function. So first function into integral of the second minus integral of derivative of first into integral of the second. Okay. Okay. So in this we have integration terms and the boundary term. If you look into this boundary term, here what are directly appearing value of f at the boundary. Boundary means y equal to 0 and y equal to a, and value of df dy at the boundary, y equal to 0 and y equal to a. I told you that the method of separation of variable will work if the boundary condition is homogeneous. So here the boundary condition on f and df dy are homogeneous at a and 0 respectively. So at y equal to 0 you have df dy equal to 0, and at y equal to a you have f equal to 0, if you recall. So that means this boundary term is getting 0, and this boundary term is getting 0 just because of the homogeneous boundary condition. Otherwise, it at the end of manipulation it may turn out to be effectively 0 cancelled with something, but we cannot ensure that from the beginning. But when either of f or df dy is 0 at the boundaries, this boundary term can be ensured to be 0 from the first step itself, and that is the importance of having homogeneous boundary conditions in the derivation. So this is what we get from here. Next, what we do is that we simply swap m and n and write another equation. M and n are arbitrary symbols. So if you swap m and n, plus lambda m square and now you subtract these two. These two you subtract. So if you subtract these two, this will be cancelled. This, because it is just the same thing, very symmetric terms. So, and from these two terms, you can get that lambda n square minus lambda n square integral of fn fm dy. This is equal to 0. Now, what we can conclude from here? So, when n is not equal to m, then obviously this is non-zero, and therefore from here we can conclude that integral of fn fm dy is 0 if n not equal to m, if they are not equal, and if n and m are equal, then this term will become 0. So there is you in general you cannot say that it will be 0 under that condition, because anyway this is 0, product will be 0. So the other is not assured to be 0. So we can just simply say that it is not equal to 0 otherwise. You can also consider it equal to 0 for even m equal to n, but that will give a trivial solution, that the function u2 altogether will be 0. That is not the case that we are looking for. So this is something which we can make use of. This is called as orthogonality condition. All of you have learned this from Fourier series formula, and that is why I mean it may be easier or more difficult as a student to remember this, because these are at the end formula. So depending on how serious student you are and how much you love mugging up things and memorizing. Depending on that, you can remember or you can forget. But there is no credit or discredit out of that. I mean, you are entitled to remember and forget things. But here we have not, I have never even touched upon the terminology Fourier series. So what is coming up here is naturally a Fourier series by something which is a fundamentally considered derivation. So this orthogonality condition, again you see that orthogonality, when we say orthogonality of vectors, I'm just drawing an analogy of orthogonality of vectors and orthogonality of functions. So when we have orthogonality of vectors, say two vectors, A and B. Their orthogonal means, vector can have n components mathematically. Just to give you a geometric simplicity and you can visualize, let us say the vector has three components, x, y, and z. So orthogonality means in that geometric space they are perpendicular. So if they are perpendicular, their dot product will be 0. So how do you calculate dot product? You multiply the corresponding components. So x component is one component, a1 b1 plus a2 b2 plus a3 b3. That is equal to 0. In the Einstein's index notation, it is ai bi equal. Right. So that is the hallmark of this orthogonality of two vectors. Similarly, this is orthogonality of two functions, very similar. So function fn, and it may also be multiplied with a weight function which is equal to 1 in this case, and this integral is equal to this one is called as inner product instead of this dot product, a more general definition, and that is equal to 0. So this is called as orthogonality condition. So now that we know this orthogonality condition, we will try to use this to find out an. So I will erase everything except I will just keep the orthogonality condition which we will use for finding out an. So if you recall, our u2, I mean, when we substituted the boundary condition, u2 is equal to minus u1 at z is equal to b, we came up with an fn. Fn is what? Fn is this one, cos lambda n y, where lambda n is 2n plus 1 into pi by 2a. Just I am writing the symbols into gn substituted at z is equal to b, so cos h lambda n d. Okay. So effectively, this is the variable function of y. So now we will exploit this orthogonality condition. To exploit that, we have to multiply it with fm, right? So we multiply with fm. And integrate. So dy integrating from 0 to a, because we want to use this orthogonality condition. That is why we are doing this. So if we do that, right hand side, if you write see, an is not a function of the variable with respect to which it is being integrated, and cos h lambda n b is not also, but f is. So we will separate their effects, an cos h lambda n b into integral of fn fm dy 0 to a. Okay. So if you do that, then we can use this orthogonality condition that this is equal to 0 if m not equal to n. The advantage is that in that way, all these terms in the summation, except for only one term for which m is equal to n. So there is only one, this case m equal to n. All other values of n will boil down this integral to be 0. So this will become only one term, cos h lambda n v into integral of fn square dy 0 to a. And because with m equal to n it happens, so left hand side integral 0 to a u1y into fn dy. So fn is what? Fn is cos lambda n y. So let us just recall this. This is cos lambda n y, where value of lambda n also we know, but not directly necessary for this integration. Okay. So now it is very straightforward. So this is an integral of cos square y dy, that form, as simple as a very elementary integration, and this is a parabolic function of y. This is the parallel plate solution, and multiplied with cos. So it is like y square into cos. You can keep on doing integration by parts in 2 steps to do this integration. So this will give you a value of an. You can complete this integration. You can complete this integration, and that will give you an. So that completes the solution of the problem. That what is your final overall solution? Just let us write so that we don't forget the broad picture. So you have the solution u is equal to u1, which is the parallel plate channel, which is the function of y, plus u2, which is summation of an cos lambda n y into cos h lambda n z, where lambda n is 2n plus 1 into pi by 2a. Okay, and an is what you get from this equation. Yeah. So this is the real, this is the actual rigorous solution of this problem. Now we have to see that instead of this calculation, see, this is a series calculation. In fact, this is a Fourier series. So with this series calculation, you may have to calculate number of terms to make the answer convergent, and that calculation will, for simple estimation, that will add. It is not a highly complex calculation, but it will add some elementary complexity into this entire calculation procedure. So what we would like to see is a scenario where we can compare the approximate solution, that is the this rectangular channel. There was one approximate solution we had of the form something into y square minus a square into z square minus b square u. So that solution, we constructed that solution considering certain limiting conditions. That means in the limit when it becomes a parallel plate channel, this solution will work definitely, because the form of the solution is taken from the parallel plate, corresponding parallel plates. From here we can understand that more it deviates from the parallel plate, more will be the error or deviation of this solution from this solution. So I give you a homework that how do you know that what is the deviation from parallel plate? You find out that you use the ratio of say A by B as a parameter. So you plot this U as a function of Y and or maybe let us say as a function of both Y and Z. So U as a function of Y and Z, you make a surface plot. So as a function of Y and Z, you can make a surface plot of this equation star, plot star, and also plot this equation, which is double star. For different values of different ratios of A by B. And try to show that when they agree and when they do not agree. It is very intuitive. Without even drawing this graph, I can say from the scientific intuition that they will agree well when A by B tends to 0 or A by B is very large, tends to infinity. Infinity means quite large. Maybe A by B is equal to 100, 200, around that can be considered as large. So these large limits are parallel plate limits. And because of that, they will tend to agree. But if you deviate from that, the disagreement between these two plots will be quite severe. And from common sense, therefore, we can say that the disagreement is maximum when A and B are, exactly comparable, very similar, not one of them much or even, larger or smaller than the other. So when A by B equal to 1, that is a square section channel, possibly you will get the maximum deviation between these two. But this is what I am saying from scientific bias. But you have to make a plot of this as your homework. So plot the actual solution, plot the approximate solution. Plot means it will be a surface because plot because it's a function of two variables, and show the agreement or the disagreement for different values of A by B ratio. So that will give you a clear summarized understanding in terms of the difference between a parallel plate channel solution and a general rectangular channel solution, which in a limiting case will boil down to parallel plate channel. So with this, let us close this class. We will continue with the next discussion in the next class, that is on the coming Monday. If you have questions, you can put up, or otherwise we will conclude today's class and continue this on the next day. Any question? Any of you have any question? If not, we'll close today's class and we'll meet on the coming Monday as per our usual class schedule. Thank you.